Hello and welcome back to Calculus 1 after technical difficulties, right? So derivatives of inverse trig functions. We have 6 trigonometric functions, then we have 6 inverse trigonometric functions. What's the difference? Well, we know that the inverse functions are supposed to undo calculations that functions would do. Not every function has an inverse function because we can't undo everything we do in life. For instance, shatter the vase or a plate or a glass, you really can't put that together. If you put on a sweater, you can take off the sweater. So there you go. So technically, in a nutshell, inverse would undo the operations of the original function. Turn light on and off, put the sweater on and off, get in a car, get out of car, drive home, drive back, right? I mean, drive to school, drive back home. Right? Certain things can be undone, but then again, certain things like you put too much salt in a soup, right? Unless you move your soup to the bathtub somehow and then heat that up to dilute all the salt you put, right? Your soup is ruined. So, in general, sine of an angle is a number, and then inverse sine of a number is an angle. So the examples of this would be obviously sine of, let's say, 30 degrees is equal to 1/2, and then inverse sine of 1/2 is 30 degrees. Now you can go and work with any of these. So we know how to find 6 derivatives for trigonometric functions. The question is, what are these derivatives for inverse trig functions? Now they can be derived by using implicit differentiation. The derivation is in a book if you're interested. This is not an honors course with proofs, so we'll skip over that part and write the formulas down, see which way we use them. If you're interested, obviously, in the next level, stop by. Stay after class, we can discuss that. And it's in the book, too. So, what are these? Well, we want to know the derivative of sine inverse. This is one of the important ones, which is 1 over square root of 1 minus x squared. So this is the formula for sine inverse. And then probably the most important formula of all is the tangent inverse. This one shows up a lot, especially in integration, then Calc2, then differential equations everywhere. And it is 1 over 1 plus x squared. Like that's the boss of all of them. And then we have the derivative of secant inverse of x, which is 1 over absolute x times the square root of x squared minus 1. You see, sine is 1 minus x squared and secant is x squared minus 1.
Absolute value of x, right?
Absolute value of x, yes. And now we have the other 3. You know what's beautiful about the other 3? They're the same, you just put minus sign on each one of these ones in the numerator. They're the same. So, what's the derivative of the cosine inverse? It's just going to be negative 1 over square root of 1 minus x squared. That's all it is. Same as sine, just put a minus there. The derivative of the cotangent inverse of x is negative 1 over 1 plus x squared. And finally, the derivative of cosecant inverse of x is going to be negative 1 over absolute x square root of x squared minus 1. So these are your 6. Technically, learning the 3 on the left will immediately give you 3 on the right, because they're only minus sign apart. And you have to be very careful with the chain rule on these. Other than that, they're straightforward to use. It's a formula, you plug it in, you're done. So what do I mean the chain rule? Remember how when you take the derivative of sine x, you get cosine x? But then when you take the derivative of sine ax, because of the chain rule, you get a cosine ax. First off, note that the argument didn't change. It's still ax, and you have a in front, right? And in general, if you have sine of any function of x, the answer would be f prime of x times cosine of f of x. Right? This would be the chain rule piece. So we're going to treat our. So this is a review. This is old, right? We are going to treat our inverses exactly the same way. So if I have the derivative of, let's say, inverse tangent, remember this is the most important one, you will be sick of this. Let's say you have the derivative of inverse tangent of x squared minus 5, whatever. This is now one unit. This is the entire argument of inverse tangent. So you would have 1 over 1 plus, and instead of x squared, you have to use x squared minus 5 squared times 2x, which is the chain rule. So these are the tough situations when you have to deal with the inverse trig functions that have a chain. Another problem, d dx of, let's say, I don't know, cosecant of, I don't even know what to put, inverse of, no, ln x, it doesn't matter. You can put whatever you want. Put whatever you want. So what do we get? Well, inverse cosecant is -1 divided by absolute value of the function, which is ln x, times the square root of that ln x squared minus 1, times, in the chain rule, the derivative of ln x is 1 over x. So we can have better versions of our formulas because this ln x is a function, and you can put any function in there. So technically, what would this formula be if you are to write the general case? Now, what is the formula for cosecant inverse of any function? Well, it's exactly -1 over absolute value of that function times the square root of the function squared minus 1 times the derivative of the function because of the chain rule. If you compare this one to the original formula we had, which is the cosecant -1 of x, which was -1 over absolute x, square root of x squared minus 1, notice that the formula that I gave you above, this one, is actually general case, because if I put f of x to be x, the top formula collapses to the bottom one. If f of x is x, then this f of x becomes x, this f of x squared becomes x squared, and the derivative of x is 1, so that's not even there. It collapses to that formula below. So you can recast all of the 6, right? All 6 functions. You can recast them into these f of x kind of mode, and then put anything. But it's just a chain rule where you replace x with f of x, and then every x in the formula will replace with f of x. And you have to remember, because of the chain rule, to multiply by the derivative of that f of x. That's the entire lecture.
What is the application for these formulas in like engineering?
Well, inverse tangent is going to show up a lot first, then inverse sine, in engineering, you are calculating the total energy, which will be the integral, depending on what your functions look like, right? How much energy is supplied to the system and so on. So if it matches the inverse tangent graph, you're integrating inverse tangent, the integral of inverse tangent. I mean, the integral of the thing will be the inverse tangent. Okay. So there are many applications for these things. You just, need. That's why you're taking other classes. Mathematics does this in general, right? Mm-hmm. And I understand that a lot of this stuff is, disassociated from things. But you know what? My favorite section, 311, is next. Mm-hmm. So it's all word problems and application. So we're going to see some of this stuff used. But again, when you are transferring out in whatever engineering you belong to, and you're taking 300 and 400 level courses, students constantly tell me, oh my God, it's just calculus over calculus upon calculus upon calculus. And I said, yes, it is. You have to do it. And obviously it actually builds up much higher than that. Let's do one more example from homework. I'm going to pick something from textbook. Practice exercises 13 through 40. This part over here has 13 to 27. Give me a number, 13 to 27.
23.
23. Cotangent inverse of square root of z. Find the derivative in respect to z of cotangent inverse of square root of z. This is problem 23 in a textbook. Okay. Cotangent is the same as tangent with a negative 1. So I have negative 1 on top, 1 plus, and I have to square the original function. Well, that's just going to be z, because square root of z squared is just z. And then I have to multiply this by the derivative of the function, which is 1 over 2 root z. So the total over here is negative 1 over 2 root z times 1 plus z. That's the derivative. That's the answer. These problems are very quick if you know the formulas. So inverse tangent is the most important, followed by inverse sine, followed by the other 4, which are very rare. Unless it's a targeted problem like this, then it's probable, right? Ta-da! Bye. Next section.